system of virtual work. So I spent some time on this principle of virtual work. So that principle is used for deriving the expression for dummy load method of finding the displacement. I'll state the principle and I will straight away give the expression for dummy load methods, which we can straight away use for working problems. So here again, consider a linearly elastic structure, linearly elastic structure subjected to a system of external forces, subjected to a system of external real forces F, resulting in a system of, resulting in a corresponding system of real displacements, delta real, both are here. A force F, that is given applied force, which causes a displacement delta. You can measure it and you can see it. That is called real force, real displacements. Then the product F delta is defined as real work. That is by definition of work done, force into displacement. So that is called real work. Now, the virtual work means it is an imaginary or dummy or fictitious force applied, causing fictitious displacement or imaginary displacement. As you have seen conjugate beam method, it is an imaginary beam. It's similar to your original real beam. Here we say virtual work. So on account of virtual force or imaginary or fictitious force and fictitious displacement. So it is called real work. So if the structure is subjected to a fictitious or imaginary or dummy. It's a dummy thing. Fictitious, imaginary, or one and the same word. Even imaginary or dummy system of forces Q. That force I will denote by the symbol Q. Real force F. Q I will use the symbol for representing virtual force resulting in virtual, because force is virtual, displacement also has to be virtual displacement delta. That virtual displacement I will call it as delta. Here it is big delta, there it is small delta. Then the product, here you have to be careful. The product, it's the cross product. Q multiplied by real displacement. Q delta, virtual force, multiplied by real displacement. Then the product Q delta or real force F multiplied by virtual displacement. It is a cross product. The product Q delta or F delta is defined as the virtual work. Both these cross products we define as a virtual work. After all, work is nothing but force into displacement. Here, virtual force multiplied by real displacement or real force multiplied by virtual displacement, that we call it as a virtual work. Here it is pure work, it is or real work is product of real force, real displacement. Here virtual work is the product of either virtual force, real displacement or real force and virtual displacement. This is the definition of virtual work. It is nothing but product of force and displacement in the earth. Which force, which displacement, I have defined here. That is virtual work. Next, principle of virtual work. So this principle of virtual work you can always visualize or think in terms of two things. One is principle of virtual forces, another principle of virtual displacements, because it is always cross-product. That's why we have the principle of virtual work. You can ideally see it as two definitions. One is principle of virtual forces, another principle of virtual displacement. So that is nothing but this total work done has to be zero, both external and internal, because external has to be work done should be equal to internal and opposite. So therefore that sum should be zero. That's all the principle of virtual work. Because it has to be in equilibrium. Whatever external work done should be internal energy, or in other words, the external and internal work should be zero, because one is opposite of the other, it should be equal. That's all the principle of virtual force and virtual displacement in terms of these expressions. So next you can say the principle of virtual work. The principle of virtual work can be defined as in terms of one principle of virtual forces and principle of virtual displacement. So the principle of virtual work you can just consider as made out of two principles. One is called principle of virtual force, another called principle of virtual displacement. Now I will define what is that principle. Already I told, since the structure is in equilibrium, so the total external work done should be equal to internal work done, or in other words, the sum of external and internal work done should be zero, in other words. So for now we will take up the principle of virtual forces. Principle of virtual forces. So in a linearly elastic structure, subjected to a system of virtual forces, Q, both system of forces, both external and internal. The external system of forces, we can call it as QE, virtual forces, because Q is the symbol I am using, external, and internal QI, both external and internal, virtual forces. Q is the symbol I am using. This E stands for external force, I stands for internal forces acting through a system of real, because it is with respect to virtual or principle, virtual work done. Virtual work done is always should be cross product. Here I consider virtual forces. So the corresponding displacement has to be real. That you have to be careful. Acting through a system of real displacements, both external and internal. That real displacement, I am using the symbol delta E and delta I, acting through that. So displacements, then this Q E delta E minus Q I delta I should be 0. Then Q E delta E minus Q I delta I would be 0, provided the system of forces is in equilibrium, because it has to be in equilibrium. That is, the equilibrium condition, compatibility condition should be satisfied. That you have to state. Is in equilibrium and the displacements should be compatible with the boundary conditions or constraints. Okay? Boundary conditions or constraints. So this is called principle of virtual force. On similar lines, you can define principle of virtual displacement. Same thing in a linearly elastic structure, subjected to a system of virtual displacement. Here it is virtual force, there it is corresponds to displacement. Virtual displacements, both external and internal. Symbol will be virtual displacement, small delta E delta I, acting through a system of real forces, that is F, E and Fi. So then that Fi delta Fe delta E Fi minus Fi delta I is equal to 0. That is your virtual displacement principle. And provided this holds good, provided system of forces, in general I am writing force, I am not using virtual or this, so it takes care. Forces means here it is virtual, there virtual displacement. Here forces, both should be compatible. So that also we can take. So principle of virtual on same lines. If you know one other, automatically you can define. Similar to your Castellan's theorem. They are all interrelated, one converse of the other. They are converse. One definition, you make it very clear. Automatically the other one, it follows. So principle of virtual displacement. So you can repeat in a linear elastic structure subjected to a system of virtual displacements. Virtual, because as the name itself indicates, it is the virtual displacements, both external and internal. That's symbol small delta E and delta I acting through a system of real forces. That's all the change. Real forces, both external and internal, that is Fe and Fi. Then you have this Fe delta E minus Fi delta E is equal to 0. This is the principle of virtual displacement, provided the system of forces is in equilibrium and the displacements should be compatible with respect to constraints. So this is about the principle of virtual work. Again, virtual work means principle of virtual force and virtual displacement. I have defined what is virtual work. It's a cross product. Real work is actual force displacement. This clearly you have to remember theory. What are the things I have told now? Strain energy, concept of strain energy, the expression of strain energy due to axial force, bending, then Castigliono's theorem, the two theorems, one for evaluating the forces, another for evaluating the displacements. Then principle of virtual work. So this principle of virtual work is again used in evaluating the displacements in structures by dummy load method. I'll give you that expression straight away. Remember that. Then we will go on working problems from next class onwards, problems on beams, trusses, frames. This seems to be a little bit vague, but go through it thoroughly without having any confusion in the mind. Make it clear all that symbols. F stands for real force, Q stands for virtual force, capital delta stands for virtual displacement, small delta stands, capital delta for real displacement, small delta for virtual displacement. Like that, if you remember, then of course it has to be satisfied equations of equilibrium, compatibility conditions, and it should be moreover, the important thing is it should be in equilibrium. All other things what you have already known, that same thing in terms of some equation form and using that appropriate abbreviations we are writing it. There is nothing much here. They are all same old thing what you have already done. That's equations of equilibrium, resolution, and same kind of thing. So then you can just take these small notes on the same principle of virtual work. So the principle of virtual work, this small note you can add it. This principle of virtual forces actually. Virtual forces is used in the analysis especially determination of deformations. Determination of deformations. The analysis of beams, frames, beams and frames, trusses, beams, frames and trusses using what is known as dummy load method, because it is virtual force we are using, that is dummy load in other words. All these words are same, dummy, fictitious load, even by Castigliono's theorem also, it is fictitious load. Here it is dummy load, unit load we are considering. It is using dummy load method or unit load method. It's also called as unit load method. So the expression used for that delta, similar to Castigliono's theorem I told, here by dummy load method or virtual work method, the expression used is this KIL divided by KGI. This is for results. Here it is delta U by delta U, that ratio. This is nothing but the your K, PK. Here also PK, Li should come there. Fi square, that if you differentiate 2Fi, delta Fi by that, Li is there, that will not. But that 2 to get cancelled, we'll have only this same expression. Only the derivative is replaced by unit load force. That's all, nothing other than that. So, and is delta for beams and frames, it is mx, small mx, mx ds by di, A of that particular member. This is for beams and frames. You can remember this expression. Where not Pi, Fi. Other things are also here. If Ki is the force due to unit application of the load, dummy load. Again, you have to do the analysis. Fi is the force due to given external load. Ki is the force in the truss due to unit load applied at the point or at the coordinate where deflection is required at any coordinate j. There you have to apply a unit load Kj. Here also it is the section due to unit load. Unit load you have to apply at that section. This again I will explain it and I take up the problem. This much expression you have to remember. One Castellan theorem and the corresponding expression. Another is dummy load method, which is derived from principle of virtual work method. So these expressions, if you remember, and the derivation, whatever I have told, that you can work problems on trusses and beams. From next class onwards, we will take up problems on beams, trusses, beams. That completes your unit 4, if I want problems.